Hi students, welcome to section 3.2, the mean value theorem and Rolle's theorem. We are continuing today with applying the derivatives that we learned. Again, there won't be any new derivative calculations. We're just going to be applying the derivative. We're going to be doing the mean value theorem and Rolle's theorem today. Notice I kind of have little quotes on the O's and we'll talk about that. Your book actually does the Rolle's theorem first and then the mean value theorem. That is wrong, I believe. And here's why, is the Rolle's theorem is actually one condition of the mean value theorem. So you should learn the mean value theorem first. Now these theorems are really understandable, I think, and in the real world, like there's many situations that match them. And so let's go ahead and take a look at it. This is the notes video. I'll also be posting an examples video using my writing tablet. So you'll be watching both of those. Okay, so the MVT, the mean value theorem, says these conditions. And again, we have to meet these conditions to be able to use this theorem, right? We've seen that in the past where we've had theorems where do we meet the conditions, then we can use it, right? The intermediate value theorem, or do we not meet these conditions and so we just can't use it? And we say so is up. So for the mean value theorem, let a function be differentiable and continuous on the closed interval AB. Now, let's talk about that. Your book does say differentiable and continuous, but you know that differentiable also implies continuity, right? Continuity has to exist if a function is differentiable. There has to be on a closed interval, but it's continuous on a closed interval and differentiable on the open interval. Again, this is a kind of a small point. Why? Is because continuous can happen on a closed interval. Differentiable has to happen on an open interval, right? Because you have to be able to, to have differentiability, to have a derivative at a point, you have to be able to determine the slope from the left and the right of that point, and you can't do that on a closed interval. I can't approach A from the left or B from the right, but on an open interval we can. So it's really a small point that we're making. But if a function is differentiable and continuous on a closed interval, there exists at least one x value on the closed interval where if you found the average rate of change on that interval A to B, that somewhere there is a derivative at some x value C in AB that has the same derivative as the average rate of change over the function. Okay, so again, we have the average rate of change. You can see this as a slope formula. Okay, let's look at a picture of that. Notice I made a function in black that is differentiable and continuous on this closed interval A to B. Okay. Notice what I did is I connected f of A to f of B, right? These 2 points, and drew a line. And if I asked you to find the slope of that line, that would be the average rate of change, and you would use this formula, right? So the slope of this line is the slope here, okay? Notice that on the interval from A to B, that right here at this point, this x equals C, that I was able to draw a tangent line whose slope, that's a derivative, slope of a tangent line, is equal to this average rate of change. They're obviously parallel. So that must happen at least once on the interval from A to B. Notice on this interval, it happens twice. Notice at this C here, that when I drew the tangent line, that its slope was also parallel to the average rate of change. So again, if you have a function that's differentiable on an open interval, continuous on a closed interval, there exists at least one x where the derivative equals the average rate of change. It says, ask me about 50 miles per hour. What does that mean? That means imagine that you are on a trip and at hour 1, you're going 40 miles an hour. And at hour 2, you're going 60 miles an hour. Notice that your average speed over that time was 50 miles per hour. Now, logically, doesn't it have to be that at some point between hour 1 and 2 that you were going exactly 50 miles an hour, right? Because driving in a car, your speed is differentiable and continuous, right? So think about that. If you're first going 40 and then at the end you're going 60, to accelerate to 60, you had to go through 50, right? Or let's say that you dropped below 40 miles per hour. Well, at some point you had to go above 50 miles per hour, right? To get to the 60 or to get an average speed of 50, right? You had to be, if you drop below 40 miles an hour, you had to be going faster than 50 at some point to bring that average up to 50. Or maybe you did it many times between 40 and 60, right? Or more. So it makes sense, again, that if you're going 40 to begin and 60 to end, somewhere you had to be going exactly 50, right? So the average 50, the derivative 50. Okay, now let's see what else I forgot. Oh, how do you use this? Here's the steps to apply the mean value theorem, right? F of x is continuous and differentiable on a closed interval AB. The next thing I do is I find the slope, I find the average rate of change, then I find the derivative of the function, set it equal to the slope, find the x where it happens, okay? Rolle's theorem. Now what Rolle's theorem says is it's all the same conditions as the mean value theorem, continuous differentiable on a closed interval, but f of a equals f of b. Your starting value equals your ending value. So what happens there is when these two values equal each other, then of course f of b minus f of a, you have some value minus that value. Of course you're going to get a 0 in the numerator. Of course the average rate of change is 0. So in Rolle's theorem, you can hear that O, you can hear that 0. That's why I have these quotes here. So it's really just a special condition of the mean value theorem. So you are finding an x equals c where the derivative equals 0. It is guaranteed if a function is differentiable and continuous on a closed interval, and f of a equals f of b, somewhere is guaranteed that at some x the derivative equals 0. Okay, here's some examples here. Take a look. AB, AB. Notice on all of these pictures, I drew black functions in black that are continuous and differentiable. And notice right here, right, between A and B, here's where the tangent line has a slope of 0. The derivative is 0. Notice here, right, guaranteed. Right, here's where the tangent line has a slope of 0. Notice here, you may say, well, what's going on here? Well, what if f of a equals f of b and you just stayed at that value all the time? Notice that the derivative is 0 everywhere, right? Or it could happen more than once at more than one x, right? Here's where the derivative is 0. Here's where a derivative equals 0. And it says, again, ask me about 50 miles per hour. So again, isn't it true that if at the beginning, at 1 hour, you're going 50 miles an hour, and at hour 2, you're going 50 miles an hour, right? That, right, f of a equals f of b. Didn't it have to be somewhere, right, where the derivative was 0, right? Either you started at 50 and you accelerated and went back down to 50, creating a derivative right here. Or maybe you started at 50 and went below 50 miles an hour and came back up, making a derivative here. Maybe you stayed at 50 the whole time, right? Here, maybe you went above 50 and below 50 sometimes, right? So all of those conditions produce Rolle's theorem. So thanks for hanging out with me on the notes. And now I'm going to do an example video for you based on these problems.